Hey everyone, so today we're going to talk about other ways to describe elements within a data set, descriptive statistics such as percentiles, quartiles, and outliers, and we'll look at a way that we can graphically depict that information in a new graph called a boxplot. Well, let's start off with percentiles. You've probably seen percentiles because we've all been exposed to standardized testing where they usually tell you how you performed in what percentile that you scored in. For instance, if you scored in the 50th percentile, 50, then you scored right in the middle. Half of individuals scored higher than you, and you scored higher than the other half. Similarly, on another note, for example, if a person is in the 90th percentile with regards to their height, then they're probably quite tall because they would be taller than 90% of other people that you would run into. And as a quick digression here, I just Googled 90th percentile height, and sure enough, there are some statistics regarding this for the population of adults in the United States. And it appears that the 90th percentile for male heights is about a little over 6 feet, almost 6'1", and for women's height that would be just shy of 5'7". Just kind of a fun little digression there. But let's look at some common percentiles. Some very common percentiles would be the 25th, the 50th, and the 75th percentile. They are so common that we would even call them the first, second, and third quartile. And even more so, we abbreviate those commonly as Q1, Q2, and Q3. And we actually already have a name for Q2 because that's the 50th percentile, or the second quarter. It is also known as the median. I would like to do a quick depiction of what these percentiles might look like in a hypothetical data set. And I'm going to do that on a number line here. Let's suppose that over here on the left is our smallest value, I'll call the minimum, and over here is our largest value, the maximum. Now, I don't really need to put numbers on these, but if you wanted to, just for fun, let's call this 0 and let's call this 10. Just some nice numbers. Let's consider where the median and the quartiles could land. The median could land anywhere. And just to exaggerate this fact, I'm going to put the median over here. Q2. So half of the values in this data set are to the left of this median, and the other half are above it. Similarly with the first quartile, that doesn't need to be in the middle of this segment here. It can be, I'm going to exaggerate again, maybe right there. And similarly with the third quartile, I'm going to put you right here to exaggerate. The quartiles divide our data set into quarters. There is 25% of the information is between the smallest value and the first quartile. There's also 25% of information from the third quartile there to the maximum. 25%. And similarly between each of these quartiles, I think I can fit it, those segments there would also contain 25% of the observations. These values, the smallest, the largest, and the three quartiles, can give you a good sense of how a data set is distributed. Furthermore, sometimes those 5 values are reported, and sometimes they're called the 5-number summary. And the 5 values that make up the 5-number summary are the minimum, the maximum, I'll put them in order. The first quartile, the second quartile, aka the median, and the third quartile. So those are the 5 values that make up the 5-number summary from smallest to largest. Right along with the 5-number summary, we've got what's called the interquartile range, which is a measure of how spread out the data set is. It is the range of the middle 50% of the observations. If we look at our little image up here, the middle 50% would span from the first to the third quartile. And so that's what the IQR is. It is the range between the 2 quartiles, the third minus the first quartile. So all this information, 5-number summary, interquartile range, it's giving you a sense of how a data set is distributed. It is summarizing a lot of information. Moving right along, let's discuss the concept of outliers, which in a statistical perspective, these are extreme values or observations in a data set. And outliers can occur in one of 2 ways. An outlier can be an extremely small value relative to the rest of the data set, or extremely large. And we need to have some sort of way to distinguish outliers from the rest of the data set. As such, we have 2 thresholds. They're actually called fences. We have a lower fence and an upper fence. And these are the thresholds that are going to allow us to distinguish outliers. Let's start with the lower fence. We need to get to the lower spectrum of the data set, and that's given by the first quartile. But that can't be it. We can't have a quarter of the data be an outlier every time. We need to get a little smaller than that. Subtract 1.5, that's just a part of the formula, times the IQR. And what this is going to do, it's going to take you to the lower quarter of the data set and go a little bit lower, some specified systematic amount. And any value that's smaller than the lower fence will be an outlier. So the upper fence is defined very similarly, but it needs to be in regards to the upper end of the data set. So instead of Q1, this is going to be the third quartile plus 1.5 times the IQR. Putting that in writing here, a value that is larger than the upper fence or smaller than the lower fence would be considered outliers. And there can be no outliers in a data set. There might be one or multiple. There's no rule about that. Let's put all of these topics together in the context of an example. All right, I've got some data loaded in here, and this is representing the number of inches of rain in Chicago, Illinois during the month of April for 20 randomly selected years. And we're going to do several things here, but first we're going to determine the median and the quartiles. Let's start with the median first, and that's because it's a little easier to do right off the bat. So the second quartile. Now remember, we need these values to be arranged in ascending order first. Luckily, I've already done that for us, so we've saved ourselves a little bit of work there. But that's an important first step. Recall, with an even number in our data set, our sample size is 20. When we determine the median, it's not going to land on one value. It's going to be a tie between two values. Namely, if you kind of do the naive method, you're going to find that it's going to be tied between 4.02 and 4.0. Therefore, the median is the average between those two values. And I don't think that's too difficult to see that that would be 4.01 inches of rain. Alternatively, if you wanted to use the formulaic approach to finding this median, remember we have this funny little formula which refers to the value that's positioned in the middle. With 20 as our sample size, 21 chopped in half is the 10.5th value, which, count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would be a tie between the 10th and 11th value, which is exactly what we've determined here. So that's a good time. Let's move on to the first quartile. There's a couple ways to do this, but I think I want to show you an intuitive approach. Because we found the median, which is the 50th percentile, well, isn't the first quartile half of 50? So for a brief moment here, I want to ignore the upper half of the data set. Right now, all that is displayed is the lower half, the bottom 50% of the data set. Let's take the median of the values that are shown. That would get us the halfway part of the lower half. Half of a half is a quarter. And again, there's 10 values shown, so it's not going to land on a unique value, but will be tied between two values. I believe these two. Therefore, we need to take the average between these two numbers to get the first quartile. So the average of 2.47 and 3.41 is 2.94 inches. Another way to accomplish this in a more formulaic approach would be here dividing by 2 gets you the halfway mark. But if you divide by 4, then you get the quarter mark. And that would get you a slightly different answer. That's usually what software programs will do on Google Sheets or Excel. But that's a more formulaic approach to calculating the first quartile. And more technically, this approach that we did, if it's intuitive to you, then stick with it. But technically, that's an approximation. Let's move along to determining the third quartile. The logic here will be the same. Now I've displayed the entire data set again, but the third quartile can be found by taking the median of the upper half of the data set. Something that's kind of nice the way I've stacked these 20 values is it's again going to be a tie, but this time between these two values. So we want to average up 5.5 and 5.79. Cool. So again, that would be kind of an intuitive way to approximate the third quartile. But if you wanted a more formulaic approach, then what we would do, kind of similar here, the median, it's chopped in half. Here this is divided by 4 for the first quartile. For the third quartile, this is actually 3 quarters. So 3 times n plus 1 over 4. Now that we have our estimates for the first, second, and third quartile, let's go and compute the interquartile range, and then we'll see if there are outliers in this data set. The range of the third and the first quartile, we must subtract the first quartile from the third quartile. For us, we have those values right here. Therefore, our interquartile range is about 2.705. Scrolling down here, let's determine, based on all this info, if there are outliers present in this data set. We need to utilize our formulas from earlier, that of the lower fence and the upper fence. Let's start with the lower fence first. We're going to take our first quartile and subtract 1.5 times the IQR. And remember the order of operations here. We are going to perform the multiplication first and then the subtraction. So just to make that clear here, we need to perform this multiplication, 2.705 times 1.5. That gets us 4.0575. And now we will perform the subtraction. This looks like it's going to go to a negative number, negative 1.1175. If we consider what is an outlier would have to be smaller than negative 1.1175. Do we have any negative numbers up here? No, because this is rain. So there are no outliers on the smaller side of our data set. But we're only halfway done. We now need to go check the upper fence. This formula is very similar. But this time we have the third quartile plus 1.5 times the IQR. Therefore, this will be 5.645 plus that same amount from up here. So pardon me for using my previous work to save a moment of time. Our upper fence is then going to be 9.7025. Let's go look at our data set and ask ourselves, are there any values larger than 9.7025? Oh, up here. The 10.01 is larger, but is that larger? No. So 10.01 is going to be an outlier because it is larger than the upper fence. So the 10.1 is greater than the upper fence. which makes it an outlier. So to answer this question, are there any outliers? I'll say yes, 10.1 inches. Now that we've done a lot of work here, we've described this data set almost to death, and we've got all this info here. But a picture, as they say, is worth 1,000 words or numbers. What we're going to do is draw what is called a box plot. A box plot is a new graph for us, and it utilizes all this information to create it. So namely, we're going to see the 5-number summary along with any outliers that exist. I'm going to copy and paste a grid here, and we will draw our box plot next to this grid. Typically, these are drawn vertically, which is why I've put this axis vertically, but this could also be created in a horizontal fashion. Okay, like I had mentioned, the 5-number summary is going to be displayed. And there's going to be a box in this box plot. The box is going to encapsulate the quartiles. So I'm going to put a little notch here at the first quartile, which was a 2.94, just shy of 3. The second quartile, the median, was just barely bigger than a 4, and the third quartile, 5.645. That's going to give me my box. That's the box part, and I'm going to annotate this when I'm completely done. The maximum and minimum are going to be displayed along with outliers. The minimum of our data set, let's scroll back up, was a 0.97. And there was no outliers down here, so I don't need to worry about that for the moment. I'm going to mark my minimum, 0.97, right around there, and I'm going to extend a line to that minimum. Cool. Now here comes the fun part with the outlier. We did mention that an outlier was present in the data set at 10.1. So I'm going to mark that with an asterisk. That is common. And that happens to be the maximum, but I still need to depict the upper tail or the right tail, and that right tail needs to extend to the next largest value. That's not an outlier. We need to go look at our data set again. The next largest value that is not an outlier is a 9.69. So that is where the upper tail will extend to, 9.69. Right around here. And I will extend to the box. Ta-da! That's our box plot. Now I want to annotate this so that way it is clear for your notes. The edges of the box are the quartiles. This lower tail or left tail, because there's no outliers, this is extending to the minimum. This is where it's fun. The outlier was represented with an asterisk, very common. But now, where do you extend this upper tail? That goes to the next largest value. That is not an outlier. And in this case, that was 9.69 inches. there's one thing that is missing from our graph. Can you tell what it is? Well, usually we like to label our graphs. This green labeling is not necessary, that is for your benefit, but we like to label the axis. So this should say rain amount in inches. Now I'm pretty happy. Can you tell what kind of shape is present in this distribution? Is it bell-shaped? Is it skewed? Well, if it was bell-shaped, then the left or lower tail would be pretty similar to the upper or right tail. And it kind of seems like the right tail is a bit larger. So can you tell what the shape probably is? It is skewed to the right. And that's going to conclude this video here. Hope you enjoyed it. Boxplots, quartiles, percentiles.